This is lecture 6 of our course EEE 4705 microcontroller based system design. In this lecture we will try to understand some of the arithmetic and logic instructions we have in 8051 assembly. So let us start. So first of all, we will look at one example we have already seen before. Maybe you have also seen that in your quiz. Here we will try to add two unsigned numbers, and after the addition how they affect different flags, we will try to look at those. Okay, so first of all, let us try to add these two numbers. So 1 1 becomes 0 here with a carry, 1 1 again 0, then 1 1 again 0, 1 1 again 0, 1 1 again 0. So in this way all the values will be 0 because every time there is a carry, and finally the ninth bit is actually the carry here, right? Okay, so we can understand obviously because there is a carry here, so cy flag should be 1, and P or parity flag is whenever we have odd numbers of 1 in the result. Actually the result here is this 8 bits, you have to remember. Okay, this is the result of register A, not the ninth bit, and if that is the case, then we have no ones here, or we don't have odd numbers of 1 here, so we can say parity should be equal to 0. And then auxiliary carry also, we can say from the 4th bit to 5th bit there was a carry whenever we actually did the calculation, so this value should also be 1, right? So this is the result. Next we will look at another problem. Here they're saying assume that RAM locations 40 to 44, these 5 locations have following values. These are the values, you see, for each of the locations we have hexadecimal values stored in each of the RAM locations. We have to write a program to find the sum of the values. At the end of the program, register A should contain the low byte and R7 should contain the high byte. All the values are in hex. Okay, so here we are asked to add multiple values together, hexadecimal value, and we have seen examples like that whenever we have multiple values to add. How we actually deal with that in 8051 is because these values are 8 bits, whenever we add multiple values the result can exceed 8-bit bound, right? So what we do, we basically add two values at a time. So maybe for example here we can maybe add the first two values 7D, and then with that EB. If we add the two values, then maybe there can be some carry there. So if there is any carry, what we are going to do, we are going to keep another 8-bit register just for keeping track of that carry. So each time basically whenever we add two numbers, the result will be saved in register A, but if there is any carry, we will use R7 to keep track of that. Each time we get any kind of carry, we will just increment the value of R7 by 1 each time. So first of all we will add these two numbers, whatever result we have, with that we are going to add this number, then with that result we are going to add this number. In this way one by one we are going to add all of them to get the final result. But after each addition there can be some carry. If there is any carry, that will be actually taken care of by the help of this R7 register. So let us look at the solution here, the assembly program. First of all, we have stored 40H to R0 register because we are going to use indirect register addressing and fetch data from these 5 locations, right? So that's why initial RAM location is actually given here. Then because we have 5 different locations, we are going to run a loop for indirect address register. So that's why we have given 5 value to R2. And then we are clearing A so that there is no garbage value inside of A when we start calculation. And then also we are clearing R7 by giving the value of A. Currently in register A we have 0 value, so if I move that value, R7 will also be cleared. Then we will start with our loop. So here we are using indirect register addressing. So in R0 we have value 48, so in 48 RAM location whatever value we have that will be added with register A. In register A currently we have 0 value added, so these two values will be added, and after this addition if there is any carry that will be taken care of by this line. Okay, jump if not carry. So if there is no carry then we can move to this line, but if there is any carry then we have to go to the next line, which is this one, so we have to increment the value of R7. So if there is any carry, so R7 has to be incremented by 1, as I said before, and if not then we can skip this command and we can go to the next here, which will increment the RAM location, which will increment the value of R0 which is containing the RAM location, so from 40 to 41 in this way. And then we are going to go to again, because we are comparing with R2. R2 is containing this counter 5, so it will decrement by 1 each time, but this loop will run for 5 times, and each time if there is any carry that will be taken care of by this R7 increment. Okay, then let us look at addition of 16-bit numbers. So whenever we have numbers which are more than 8 bits, to take care of those additions we have to understand how actually carry helps us to solve that. Okay, so this is hexadecimal addition, and how we do this calculation. To understand that, first of all let us look at one decimal addition. Okay, so let's say we are taking two values like 37 and 49 maybe. Okay, so we are adding these two values and these are decimal values. So if I add these two values, 7 plus 9 is equal to 16, but we never write 16 directly here. What we do, because this is based on arithmetic, from this 16 we keep 10 aside and just write 6 here, and that 10 becomes 1 for the next stage, right? Here we use that as carry basically, and then we add these two things, it will be 8, right? In this way we do calculation for decimal addition. So whenever we are talking about hexadecimal, the concept is similar, but here the base is 16, so we have to think in terms of 16. So here if I add these two values, d is equal to what? D is in terms of, if I want to say decimal, so a is 10, b is 11, c is 12, d is 13, right? So 13 plus 7 should be equal to 20, right? So here if I add these two values I will get 20. Now because this is more than 16, in this base 16 calculation we have to subtract 16 from that. Okay, subtract 16 from that, whatever we have after that will be written here. So 4 will be here, and this 16 we have kept aside will be going to the next stage and will be considered as 1, like carry. Okay, then we are going to do the addition again. So here what will happen, E is equal to actually what? A is 10, B is 11, C is 12, D is 13, E is 14. So 14, 8 and 1, right? 14, 8, 1, 1. So if I look at that, 14 plus 8 plus 1 equals to what? 23. And also here we have to subtract 16 from that because this is more than 16, so the value should be what? 7. Yes, 7. So we are going to write here 7, and this 16 we have kept aside will be going to the next stage as a carry, and again we are going to do the calculation. And if you do calculation like that, you are going to see this value will be 8, and there will be another carry here, and then we are going to add these three values. That will be, this will be the result for hexadecimal addition, right? Now what you have to understand, each time we can just calculate or add two 8-bit numbers in 8051. This is 16-bit, so what we have to do, first of all we have to add these two numbers then we can move on to the next stage, right? This is how it will work. So you see, whenever we go to the next stage, if there is any carry from this stage after calculation, that should be actually be considered for the next stage calculation. Like we actually have a carry here, right? We can omit the other ones, we don't have to worry about those obviously. But here, after we have calculated for these two 8 values, after this addition, if there is any carry, that should be considered or that should be taken care of whenever we add the next two values, otherwise the value will not be correct, right? So that will be done using the help of this command called ASCII, add with carry. So what is that? You see, they are saying the same thing whatever we are looking here. So this is the 16-bit value, this is another 16-bit value, we have to add these two values. So what we are doing, we are just taking the least significant 8-bit first, E7 and 8D, right? E7 and 8D, we are adding these two values. So you see, in these two lines we are adding these two values, then moving the result into R6 as they have said. So R6 should be in the lower byte, that's why we are storing this value into R6. But after this calculation there is a carry, so CY currently after this calculation should be 1, and these should be automatically be taken care of by the help of this ASCII. So whenever we do addition with for these two values 3C and 3B, we are using ASCII. So if there was any carry in the previous calculation, previous addition, ASCII will automatically add 1 with this addition. So the result we are going to get is 3C plus 3B plus 1. That will be stored in A, okay, which is this value, right? And that will be saved in R7 as asked here. So R7 will contain the upper value and R6 will contain the lower value. So in this way we can do 16-bit calculation, and even we can scale that to 24-bit calculation, 32-bit calculation. This is possible, just we have to use ASCII. Okay, next we are going to talk about BCD or binary coded decimal, and how we can actually represent them in 8051. So what is BCD? BCD is just a form of binary to represent values starting from 0 up to 9, just for our convenience, so that we can properly look at the values, understand the values for our convenience. There are two possible ways how we represent BCD numbers in 8051. One of them is unpacked BCD, another one is packed BCD. So what is unpacked BCD? Because all of the registers we have are of 8 bits, right? So if we use 8-bit register for representing just one BCD value, that will only take 4 bits out of the 8 bits. That is called unpacked BCD. So lower nibble is actually used for that. For example, here you can see to represent 5 in BCD, we can use representation like that. Upper 4 bits are blank, but lower 4 bits are representing 5 in this way. So we can represent only one BCD per register. Obviously here we are wasting these 4 bits because this is not representing anything. So that's why we have a more efficient way to represent BCD number, which is called packed BCD. In packed BCD we can represent two BCD numbers in one register or one 8-bit memory. So something like this. Here you see 59 in BCD should be represented like this. So the upper nibble should represent one value, which is 5 here, and lower nibble should represent another value, which is 9 here. Okay, so in this way we represent two BCD numbers in one register. Now whenever we actually do calculation in packed BCD, we have to always check whether the values we are getting are actually representing packed BCD number or there is any error, and then we have to take care of that. We have to correct that somehow. Okay, so we will look some of the cases where we will do addition of two numbers. Basically we want to represent them in terms of BCD or decimal, and try to do that calculation in 8051. and in 8051 we have to do the calculation in binary, or we can also say hexadecimal. Okay, so what we have to see is, after doing the calculation, whether that is properly showing our packed BCD or not. In all of the cases we will try to check that. So first case here, you see, this is the decimal numbers, right? Two decimal numbers we can add. If I add these two numbers, we are going to get what? 8, and here we are going to get 6. Now our goal is to represent these decimal numbers into its packed BCD equivalent, right? So this number 2 and 3 will be represented by one register. One of the nibbles, the upper nibble, will represent 2 and the lower nibble will represent 3. In this way we convert a decimal number into its packed BCD format, right? So surprisingly, if you just add a h to make it a hexadecimal value, kind of like that, that will actually represent this decimal value or convert this decimal value into its packed BCD. How is that? If you want to convert that to binary, you are going to see in this value the upper nibble is actually 2, this value is actually 2, right? And this value is actually 3, which is what is the definition of packed BCD. We are representing two BCD numbers in one register, right? So actually if I just add h here, that will make this decimal into a packed BCD. That is what I'm trying to say. Okay, now let us try to calculate in this packed BCD format, try to add these values and try to look at the result, whether that is actually representing 68 or not. So how should that be? This should be 0 0 0 1 0 1 1 0. This should be the result. So here this is actually 6 and this value is actually 8. So we can say here also this result is actually 68h, right? So the packed BCD representation is actually showing the same result as the decimal, so there is no issue here. This is what we want. Both of the values should kind of match here. Now let us look at the next case, and here we are trying to add similar kind of two values. So 5 and 7, if I add these two values, that will be 2. There will be one carry and it should be 62, right? If we just add h, that will convert these two values into its packed BCD format, and now we are showing that into its binary format. We have to add these two values and check whether it is actually 62h or not. So let's try to add these two values. So this will be 0 0 1 1, then 1 0 1 0. So this is actually 5 and this is what? 1 1 0 0. This is actually 8 and 4, 12. 12 in hexadecimal is C, right? So 5C, this value is actually 5CH, right? Which is not equal to 62. So there is some issue, right? The packed BCD representation is invalid here. How to solve that? What you have to understand here, just by looking at the result, we can understand the issue is coming from this lower 8-bit, right? This stage here. So for this lower portion, the value is C, which is not a correct BCD representation. For BCD, the valid range is from 0 to 9. So somehow for this particular value we are getting the issue. So what we are going to do here now, just look at what we are doing, how it is getting solved. Later on we will explain why this is happening. So to solve that, what we do, we add 6 in this stage, or in other words, we actually add 0 6 here. Okay, 0 6 here, because the problem is arising for 6, we are going to add in the same stage a 6. If there was any error in 5, we could have added 6 0. So in this way we are going to add a value with that and try to look at the result whether that solves the problem or not. So here also let us try to do the same thing. So we are adding 0 6, right? So 0 0 0 0 0 1 1 0, this is 0 6. So if I add these two value, now what we are going to get, 0 1 0 0, then 0 1 1 0. So this value is actually 6 and 2, which is what we want. So 62H is the result, which is the same value here, right? So this is correct BCD representation. Just by adding 0 6 we have solved that problem. Now let us look at another case. In this case we are going to add these two values, so 5 and 5 7 is equal to 1 2. So 125 is the result. We are representing that into its packed BCD form and then converting that to binary. So if you add these two values, so you are going to add 1 here, then 0, then 1, then 0 0 0 1 1. So this is C and this is 5. So here the values are C5H, which is not equal to 125, right? So how to solve that? So because this problem is arising in the upper byte, so we are going to add 60 now, 60H, and try to look at the result. So same thing here also, we are going to add 60 here. So 0 1 1 0 0 0 0 0. So if I do that, then look at the result, I'm going to get something like this: 1 1 1 0 1 1 0 again, and we will have a carry here, right? This one. So this portion, these 4 bits are representing 5, this is 2, and this one you can add 3 zeros with that and consider that as another value, another packed BCD, right? BCD basically. So you see here also, by adding this 60, this is solving our problem, and the result we are getting is looking exactly like the decimal representation, right? Okay, next case 4, add these two values, 7, then there is a carry with that 67. This is packed BCD, this is the binary representation. If I add these two values, 1 0 0 0 0 1 1 0. So this is 6 and this is 1, right? Which is not the correct representation. 61H is not correct. So we have to add something here. So here how we are going to understand what to add, whether 0 6 or 6 0. So because if you remember, there was a carry from the 4th bit to 5th bit, or there was an auxiliary carry, right? In this particular addition, it will actually indicate us we have to solve for the lower byte here. There is some issue at the lower byte. To solve that, we have to add 6 or 0 6 here. Okay, because we don't have any carry here, we can give 0 here, 0 6 will be added, and after I add these two values, you can understand it will be 67, right? 67H, and which is similar representation as the decimal value we have, right? So in this way we can solve. So based on the cases we have seen here, can we actually form an algorithm how to solve after addition, any kind of BCD addition, if there is any issue, how to solve that. So rule for adjustment in BCD is, after addition, if lower nibble is greater than 9 or auxiliary carry is equal to 1, then we are going to add 0.6 like we have seen. And if upper nibble is greater than 9, if that is A, B, C, D, something like that, or carry is equal to 1, then we are going to add 60H. That is the way we are going to solve that. Okay. And we don't have to manually do that in our 8051. Whenever we do any kind of BCD addition, we can actually solve that with the help of this instruction called DA, or decimal adjust. So for example, if I want to add these two packed BCD numbers, so these are actually a representation of packed BCD 4, 7 and 25. If I add them, and after that, if there is any issue, we can just write DAA. So that will resolve for any kind of issue we have for BCD addition. Next, we will talk about subtraction of unsigned number and how in 8051 we deal with that. So we will again here look at some of the cases. Before that, I think we have to understand the concept of borrow. So let us look at this decimal subtraction. Okay, so 52 and 37. So if I subtract 37 from 52, how we are going to deal with that? Basically, because this 2 is less than 7, we have to take a borrow from the next stage, and this 2 becomes 12. Then 12 minus 7 is equal to 5, and we write the 5 here. And because we have borrowed something, we have to keep that back, send that back. So this 3 becomes 4. So basically what we do, we actually do 5 minus 3, and then also an extra 1 will be subtracted here. This one is actually called borrow, right? So then we get value 15. Similar concept for binary or hexadecimal. We are going to take. So here in the first case, if I try to subtract, there is no issue. We can just simply subtract 4, and this value is 3, right? Without any issue. And we can say from the last stage, there is no borrow outside, borrow out. So we can say borrow B is equal to 0 in this case. Okay. In case 2, we are trying to subtract 96 from 62. So this value is smaller than this value. The value should be negative, right? So in this case, how we are going to take care of that? Because 2 is less than 6, we have to take some borrow. But this is base 16 calculation, so we can borrow 16 here. If I take 16 from here to here, this 2 and 16 plus 2 will become 18, right? And we are going to subtract 6 from that. We get 12, right? 12 should be here in hexadecimal format. 12 can be represented as C, so this should be C, right? Then because we have borrowed something here, we have to keep that back. So this 9 will become 10, right? So basically 10 should be subtracted, but this 6 is less than 10. So we have to again borrow something from an imaginary stage here. If I do that, what it means is we are getting a negative number. So if I take 16 from the next stage imaginarily, 16 plus 6 will be equal to 26. So 16 plus 6 will be equal to 22, minus 10 is equal to again 12, which is C. Here again we are getting C, but because we have taken something from this imaginary stage, we have to again bring that back, okay, as borrow to out stage, right? So borrow out here is equal to 1, we can say, or also we can say this particular value is indicating the value we have got at result is a negative value. Okay, this CCH is not positive value, rather this is a negative value, which is kind of counterintuitive because we are talking about unsigned numbers here, so there should be no negative values here. But this particular value microcontroller or 8051 will understand as a negative value. That's the thing. And we can check that ourselves, that the value we have got, this is not correct representation in our sense. If I want to actually look at the value, what we have to take is 2's complement from this CCH. So basically CCH is what, 1100 and 1100, right? So if you take the 2's complement of that, that will be something like 1's complement is 0 0 1 1 0 0 1 1, and we have to add 1 with that to make it 2's complemented form. So 1 1 is equal to 0, then again 1 1 is equal to 0, then 1 1, then 0, and this will be just as it is, right? So the value we have got here is 3, then 4. So you see, the value we actually should be getting is minus 34, right? Because we have subtracted the same value but just other way around. Previously it was 96 and 62, here it is 62 and 96. So previously if the result was 34, here the value should be minus 34. Okay, so if I take the 2's complement form of CCH, we are getting 34. So if this value is positive, then CCH is actually representation of minus 34. That is what I'm trying to say. So even though we are not going to give any kind of sign here, this is unsigned representation of numbers, what we are getting is, using this indication of borrow, we are going to understand the value we have got. This is not kind of correct, this is actually a negative number. If I want to actually look at the value, I have to take the 2's complement of the result. That is the idea. Okay, and I'm going to talk about these portions here later on, but let us just stick to the explanation of hexadecimal numbers for now, and then we are going to look at how in 8051 using binary these things are dealt with. Let us try to understand the same concept for 16-bit numbers. So for 16-bit numbers, if I want to subtract here, you see the same value actually. Just like before, the first 8-bit two values are 62 and 96. So here also the result should be C, C, H. But here also, because 6 is less than 9, we had taken some borrow from the next stage. We have to bring that back. That will make this 3. So 7 minus 3 will become 4, and then this will be 1. Understand? So here this borrow is actually helping, right? So here we are subtracting an additional 1 here in this stage. So this is how for 16-bit calculation it may help us, right? This kind of concept of borrow. Now let us try to understand how these calculations are dealt with in 8051. So what they do is, first of all, we are going to take the 2's complement of the subtrahend. Understand that the upper value we get is called minuend and this is subtrahend, right? So we are going to take the 2's complement of the subtrahend, then we are going to add that with minuend, because internally in any computer we don't have any architecture for subtraction. We do everything in terms of addition, whether that is multiplication, division or subtraction. We always do everything in terms of addition. So here also we are going to do the same thing. We are going to take the 2's complement of the subtrahend, then we are going to add with the minuend, and after adding everything, this is kind of new to you. So after doing the calculation, whatever the value we will have at the carry, automatically it will get inverted. To understand the concept, let us look at the first problem again. That will be clear. Okay, so here this is the value and we have shown this is the result, right? Now just to look at how 8051 deals with this calculation, we are going to convert everything to binary. So this is binary value, then this is also binary value, but for the subtrahend we have to take the 2's complement. So we have done that here, you see, just taken the 2's complement. Now we are going to add these two values, so it should be actually plus here. Okay, so positive. So after you add these two values, what will happen? 0 1 1 0, then 1 1 1 1, then again 1 1 0 1 1 1 1 1, here will go, then again 0, then 1 1 0, and there will be a carry here, right? CY. So this value is actually 3 and this value is actually 4. So we have got the value we needed, but the problem is there is a carry. After the general calculation 8051 does, the carry is 1. And you have to understand the concept of borrow we have understood for subtraction. This is done through the help of CY or carry in 8051. So that means in this calculation the value of carry should be 0, not 1, which we have got. So that's why after doing this calculation, automatically 8051 will invert the value of carry into 0. So whenever we look at the value of CY after this calculation, the value we are going to see is 0, not 1, because it will be inverted automatically. Understand? Now let us look at the next case. Here also we are going to take the binary form, then take the 2's complement of the subtrahend. We get this value. We are going to add the two values. So the result should be 0, then again 0. This should be 1. Then this value should be 1. Then this is again 0, 1 1 0, 1 1 1 1 1. So this is C and this is again C, right? So we are getting CCH, and here the value of carry flag should be 0. Now in this particular problem, because the value is negative or the value we have got is not correct in our sense, because we have taken a borrow from this imaginary stage, that's why the borrow should be 1, and in 8051 borrow is indicated by CY or carry in unsigned number subtraction, right? So from that argument, obviously this CY should have a value of 1, not 0, right? So that's why after doing this calculation, automatically CY or carry will be inverted. So from 0 it will be 1 for this case. Understand? So in both of the cases we are seeing after doing the calculation, automatically CY should be inverted. Okay, so same for this one. If I do this calculation for the lower stage, or this 8-bit value 62 and 96, after this subtraction there should be a borrow, because that borrow will help us to get subtracted in the next stage. We are going to look at this problem with the help of an assembly code, then you will understand how this actually helps. Okay, but always, all the time, this carry flag should be inverted whenever we are doing unsigned subtraction. Okay, so how actually this is dealt with in 8051? The instruction name is called SUBB. Okay, so this is the general syntax. So always, just like addition, A should be the destination and source can be anything. But generally in different microprocessors or computers, you will see there is two separate instruction, SUB and SUBB. SUB is without any kind of borrow, but whenever we are talking about SUBB, it has borrow. So it will take care of the borrow from the previous stage if there is any. Okay, for this particular example, you see, if I take the calculation for these two values, because always we do calculation in terms of 8-bit values in 8051. So that means if I want to calculate for the 16-bit subtraction, just like the example we have seen for add C, here we have to first of all do the subtraction for this 8-bit two values, 62 and 96. After that, there will be some borrow, obviously. And we are going to do the calculation for these two 8-bit values, 27 and 12. But here we have to take care of the borrow that was taken by this previous stage. So an extra one should be subtracted here in this stage. So this is actually taken care of with the help of SUPB. But the problem is, whenever we are calculating for the first stage here, in this stage, we have no possibility of borrow happening from the previous stage because there is no previous stage. This is the first stage, right? So that means for this case, initially we have to somehow make sure that an extra one is not subtracted. So that's why before we do calculation for the first stage, we have to make carry equal to 0 so that no issue happens. Understand? Because we don't have to separate instruction like SUB and SUBB like we have for addition, add and add C. Whenever we use add C, they actually take care of the carry if there is any, and they add that. And for normal addition, we don't have to worry about the carry. Yeah. Now let us look at some example programs for subtraction of unsigned numbers. So here we have to subtract 23 from 3FH, and you can see in the first line we have to first of all clear the carry so that there is no issue with the borrow. If there is some value from previous calculation, if the carry is set, then what will happen after this subtraction from 3F, we have to subtract 23, but with that an extra one will be subtracted, which is what we don't want. So that's why we have to first of all clear the value of carry before we do the subtraction here. Okay, so here in this calculation the result should be what? F minus 3 is equal to C and 3 minus 2 is equal to 1. So this is the value, and how 8051 will deal with that? It will take the binaries, subtrahend will be 2's complemented, and then we are going to get this value. So if you actually calculate that, you are going to see the result is what? So 1 is equal to 0, then 1 is equal to 0, 1 is equal to 1, 1 is equal to 1, then 1 is equal to 1, then 1 is equal to 0, 1 is equal to 0, 1 is equal to 0, then we will have a carry here, right? So Py will be initially 1, but automatically 8051 will convert that to, or invert that to 0. So the final result will be 1 here, and this value should be C, right? So 1C is the result, and carry should be equal to 0 because here automatically 8051 will invert the carry after the calculation, as we have discussed before. For the next one, you see here they're saying subtract 6E from 4C. So we are subtracting a large value from a smaller value, right? So the result should cause some issues. Initially we have cleared the value of C, then we have done the subtraction. Just understand this much, okay? Then let us look at the calculation here. So the value here actually should be minus 22H, okay? Because if you subtract 4C from 6C, the value should be 22. E minus C is equal to 2, 6 minus 4 is equal to 2, right? So if I take the calculation other way around like we have here, it should be minus 22H, but we don't get that value. The value we are going to get is, you see, if I take the binary, then take the 2's complement of the value, then calculate, you're going to see 0, then this value is 1, then 1, 1, 1, 0, 1, 1, and carry is equal to 0 here, which will be automatically converted to 1, right? To indicate that the value we have got is not correct. If I want to get the correct value, I have to take at least the 2's complement form of that, right? So here this value is actually what? D EH, right? So if you actually take the 2's complement of this value, the result we have got, let us try to do that. 1 1 0 1 1 1 1 0. So if I take the 2's complement, first of all I have to take the 1's complement, so 0 0 1 0 0 0 0 1, then add 1 with that, right? So it will become 1 0 0 0 0 0 1 0. So this is 2 and this is 2. So the value we have got currently is 22. So this value before taking 2's complement is minus 22, right? So in this way we can at least understand or get the value we want from this kind of calculation, right? So that is why what we are doing, just by looking at this carry, if that is 1, we will understand that the value is not correct, this is kind of negative value. If I want to at least look at the value which is 22 with a negative sign, we have to take the 2's complement. So that's why we have this condition, jump if not carry. If not carry, then the result is correct, no problem, we are gonna go to the next level, right? And if there is a carry, this value is negative or there is some issue with this result, then we have to take the 2's complement of the result, that will give us the value. Understand? So in this way we solve this problem. Now how it helps, how this carry or borrow helps for 16-bit calculation. Here we are taking 16-bit two values for subtraction. So we are subtracting 1296 from 2762. And here we already had seen what is the result. This value should be CC, then there was a borrow which made this one for CCH, right? Now here what will happen, if I want to do the calculation in 8051, first of all I have to subtract for these two 8-bit values. So that's why I have taken subtraction for these two values. We are subtracting 96 from 62 and that will give us a borrow. After doing this calculation, we are going to see CY carry flag should be equal to 1, as we have seen in previous examples. Whenever we subtract a larger value from a small value, the result makes the carry 1. So this carry will help us in the next stage for ASCII. Whenever we do the calculation for 27 and 12, when we subtract 12 from 27, like we have done here, it will additionally subtract 1 with the result. So the result would be something like 27 minus 12 minus 1, which is equal to 14 for A. And here only what we are doing, we are just keeping one of the values. This CC is stored in R7 and 14 is stored in R6. That is what we have done here. Other than that, everything is quite easy to understand. We have initially cleared the value of carry because in the first stage there is no possibility of any borrow coming from the previous stage because there is no stage before that. That's why we have cleared carry so that ASCII works as ASCII. Next we are going to talk about multiplication and division of unsigned numbers in 8051. So for multiplication we have this particular instruction MULAB, so byte by byte multiplication basically, but this syntax has to be fixed for multiplication. So A and B as it is should be used here, no other register can be used here other than A and B. And after this calculation, after this multiplication, the result is saved in a 16-bit form, and upper byte of that 16-bit result will be saved in register B and the lower byte will be saved in register A. So we have to be careful about that. For example, here you can see if I multiply these two values 25 and 65, the result should be E99, right? So which will be saved in a 16-bit form. The upper byte, which is 0EH, will be saved in register B and lower byte 99H will be saved in register A. Next, division. For division, similar kind of syntax, div AB. Here also the syntax should be as it is. You cannot change anything for the registers. A and B should be here as it is. And also whenever we do the calculation, numerator must be in register A and denominator must be in register B. And after this calculation is done, the result is saved in such a way so that the quotient will be saved in A and the remainder will be saved in B. Okay, so for example, we can look at this example here of assembly code. We are taking 95 as the numerator and 10 is the denominator. That's why we have saved in P. After doing the division, we will see A is storing the quotient, or basically 9 here, and the remainder should be 5 here, which will be saved in register B. Another thing, if the value of denominator or the value we save in register B, if that is equal to 0, then we will see, to indicate that error, we will have overflow equal to 1. Because if you try to divide anything by 0, that will give us infinite result or an error basically. So to indicate that, we will have this overflow flag set, otherwise the value of overflow will be 0. To understand division, let us look at this example problem. So here they are saying write a program to make port 1 as input port to get a byte of hex data in the range of 0 to FFH from port 1. Okay, so whenever we get any data from any port, that value will have a range of 0 to FFH, obviously, because we have 8 bits. In 8 bits, the result in terms of decimal, we can say 0 to up to 255 is the maximum, which is in hexadecimal 0 to FFH, right? Now our task is to convert that value we are getting from port 1 to convert it to decimal. Okay, and after we do that, we have to save the digits in R7, R6 and R5, where the least significant digit should be saved in R7. To understand that, let us try to understand the result we are going to get from port 1 will have a range of 0 to 255 in decimal. And another thing very important to understand is whenever we are talking about any kind of division or multiplication in 8051, whether we explain that in terms of decimal or hexadecimal or binary doesn't actually matter, because the result will be same. So if you actually divide, for example, 46, okay, so let's say I am dividing 46 by 5. So the result should be what? Result should be, quotient should be 9 and there should be a remainder of 1. What I'm trying to say, if you do the same calculation in terms of a binary, so if I represent 46 in binary, 5 in binary, the result should be such that we are going to get a result which is 9 in binary, or basically 1001 in binary, and remainder should be 1 basically, or 0001, whatever you say. So whether we explain everything or understand everything in decimal or binary doesn't matter, because the result we will be getting is exactly the same, just the representation is different. Okay, so now if we understand that, let us look at possible cases how we can actually solve that. So because the result we are going to get from port 1 will have a range of 0 up to 255 in decimal, we can take example of one value which is 253. Let's say, for example, 253 is coming from port 1, we have to convert that to decimal. By converting that to decimal, what we are trying to say is, if you want to actually look at the value of 253 in binary, the value is 11111101, right? So by looking at this binary value, we have no way of understanding this value is 253. So what we are going to do, we are going to use 3 different registers to store each digits of 253. 2 in one of the register, 5 in one of the register, and 3 in another register. So they will be saved in binary form, but separately in 3 different registers. This is what we are saying by converting that to decimal. 2, 5, 3 will be separately saved in R5, R6 and R7 respectively. Okay, so that is the idea. So how we are going to do that? Using division. If I divide 253 by 10, so here we should write divide by 10. Okay, so if I divide by 10, 253, we are going to get quotient equal to 25 and remainder should be 3. Okay, these 3 should be saved in R7. As we said, we are going to save 3 different digits in 3 different register. So the least significant digit will be saved in R7, which is 3. Then again we are going to divide by 10. If I divide by 10, this 25 will give us the result of 2. Quotient will be 2 and remainder will be 5. 5 will be saved in R6, and then this 2 will be saved in R5. So you see 2, 5 and 3. These three values are saved in three different registers to show us the decimal equivalent value. All of those values will be saved in binary value, but still you will understand by looking at the separate values what is the actual value in decimal. That is the idea. Okay. So how this is done in assembly code? First of all, because we will read from port 1, we have to make or configure that as input. That's why we are taking this value into A FFH and then moving that to P1 to make port 1 input. Then we are going to read from port 1 and read the value, save that onto register A. Now because we already have the value saved in A, whatever we are getting, for example in this case we got or read 253 from the port, then we are going to move 10 to B for denominator because we are going to divide A by B. If I do that, we are going to see that there will be a quotient, there will be a remainder. We are going to save the remainder onto R7. Then this Q or the value we have got here 25, this is already saved on register A because after you do the revision, the result or quotient is saved in A. So we don't have to modify anything to register A, but again move the value of 10 to register B. Then if I do the division here, A is already has the value 25 and then we are dividing that by 10. So we are going to get the value 2 as result here and remainder will be 5 according to this particular scenario, right? So right now register B has the value 5 which will be saved in R6 and Q will have the most significant digits that will be saved in R5. So in this way, in two stages, in two different division, we are going to get the 3 digits of possible values we have from 0 up to 255. Next, we are going to talk about signed numbers. So far, whatever we have discussed, multiplication, division, addition, subtraction, all of them were in terms of unsigned numbers. Now we are going to talk about signed numbers in 8051. Always any numbers we represent in 8051, they should be in terms of 8-bit. So here also the values should be represented in 8 bits. The thing is, now the most significant bit here, D7, will be representing positive or negative, indicating positive or negative number. If that is 1, that will indicate our value is negative. If that is 0, our value is positive. Other 7 bits will be representing the magnitude of that value. As a result, what will happen? The value we can actually represent with 8-bit registers for signed numbers. The range is from minus 128 to plus 127. Another thing we have to understand, all the negative numbers we represent in signed numbers are done through the help of 2's complement. So we will look at one example how that is done. For example, here you can see how to represent minus 128 for 8051. Because 8051 we have to think of 8-bit values. So first of all, we will take the binary representation of 128. So 128 in 8-bit binary is this value. We'll have to take 2's complement of that. So invert all the values 1 to 0, 0 to 1, then add 1 with that. If you do that, you are going to get this value. This is the 2's complement form of 128, or in 8051 arithmetic, in signed arithmetic, we can say this is the representation of minus 128. So this is how it works. And here we can see the binary representations of all the values for signed numbers starting from minus 128 to plus 127. Here we actually should add plus here. That will be more accurate. And here you can see minus 128 is represented by this value. Minus 1 is equal to all ones. So what we do, first of all, if I want to get the value of minus 1, we have to take 1, then take the 2's complement of that. That will give us this value for 8-bit arithmetic. Okay, so in this way all the values are shown here. Now let us look at uh, what is overflow. So why we need overflow. Sometimes what happens whenever we are working with 8-bit signed arithmetic, after the calculation, our result can get beyond the range we have. For 8-bit arithmetic, the range is from -128 to +127. If the result goes beyond that, after any kind of arithmetic calculation, that can be addition, subtraction, or anything, then obviously our 8-bit registers cannot properly show that. To indicate that error, we have to use overflow flag. This is how overflow flag helps us. And whenever that happens, this error happens, us programmers have to take care of that manually with the help of this flag, overflow flag, which is one of the bits of PSW register, if you remember, PSW.2. So we will look at this example here, okay, how that actually happens. So here, one thing to note here is we can represent signed numbers with this kind of notation. So if you just add plus here, that will automatically be considered as signed numbers, positive or negative. Okay, so if I do the calculation here, plus 96 and plus 70, that should result in a value of plus 166, right? Now if I do the same calculation in binary, you are going to see that 0 1 1 0 0 1 0 1, right? So this is the result, but this is not equal to 166 because we don't have any capacity to show 166 using 8-bit signed arithmetic. That is the problem. So somehow there is some issue in this result, and to show that, overflow flag will be set to 1. In this case, you are going to see whenever you actually look at the result and look at the overflow flag after this execution, you are going to see overflow flag is equal to 1. So how that actually happens? One thing you have to understand, in terms of signed arithmetic, this value should be considered as negative, right? So if I want to actually look at the value, what value is represented by this result, we have to take the 2's complement of this value. So 2's complement should be what? 0 1 0 1 1 0 0 1. I have taken 1's complement, then added 1 with that, so that will become what? 0 1 1 1 0 1 0 1. This is the result, right? So which is in decimal equals to 90. So the value we have got here before taking the 2's complement is minus 90, right? So which is not the correct result for this addition, we can understand, and to indicate that we have overflow flag is equal to 1. But how 8051 actually understand whether there is any overflow or not? It does that with the help of these two conditions. Okay, so whenever we do this kind of calculation, if there is any carry from D6 to D7 but no carry out from D7, this is one of the conditions. So what we mean by D6 and D7, D0, D1, D2, D3, D4, D5, D6 to D7. So if in this calculation from D6 to D7, if there is any carry but no carry from D7 to out, which would trigger a carry flag, right? If at least one of them happens. Okay, so from D6 to D7 has happened but no carry out from D7, then overflow flag should be 1. And another thing is, if a carry from D7 to out, this one, if this one happens but not this one, D6 to D7 doesn't happen but D7 to out happens, then also overflow flag should be set. In this case, what has happened? If I look at the calculation, you will see it was 1 1 0 was there, that carry was coming to the 8th bit or D7. So there was a carry from D6 to D7 in this case, but no carry from D7 to out. So first condition was fulfilled. As a result, the overflow flag is 1. We will have to understand that result cannot be shown with the help of 8-bit registers because it is out of bound. Last thing, what you have to understand, if both of the things happen, let's say in some calculation, if a carry from d6 to d7 happened and also a carry from d7 to out, that also happened, which triggered a carry flag to be set. If both of the things happen, also then overflow flag should be 0, not 1. So 4 condition. If none of them happens, if there is no carry, overflow flag should be 0. If a carry from d6 to d7 happens but no carry from d7 to out, carry should happen. If a carry from d7 to out happens but no carry from d6 to d7, carry should also happen. But if both of the things happen, that means a carry from d6 to d7, also a carry from d7 to d out. If both of the things happen, then overflow flag should be 0. So with the help of some examples, we will try to understand this condition. So here in this particular example, again you see we can represent sign numbers with the help of this kind of notations. That is possible. Now if you add these two values, the result should be minus 130, which is out of bound of our 8-bit registers, right? So the result should be incorrect, obviously. So let us try to look at the result first. 0 1 1 1 1 1 1 1 1 0. There should be a carry here, right? So there is a carry. So there is a carry from d7 to out, but no carry from d6 to d7, right? So overflow flag should be 1 here to indicate that the result is not correct. Next, let us look at this problem. So minus 2 and minus 5, if I add these two values, the result should be 7, which should be inside our bound, which should be within our range. So if I do the calculation here, the result should be valid. So how is that? So 1 1 1 0 1 1 0 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1, and there is a carry 1, right? So here in this case there was a carry from d6 to d7, as well as from d7 to out there was a carry, which has triggered this carry flag to 1. So both of the conditions are actually made here. So if both of the things happen, both of the carries happen, then we have to say overflow flag is equal to 0, indicating there is no error. So the result we have got here should be correct, which should be minus 7. Let us actually check that. If I take the 2's complement of that, it should be 0 0 0 0 and 0 1 1 0, right? If I add 1 with that, that will become the 2's complement form of this value. So 0 0 0 0 0 1 1 1. So this value is actually 7. So that means before taking the 2's complement, this value was actually minus 7, the value we want. So the value is correct, we have got, even after getting 2 flags, because the overflow flag is 0. Next we will look at some logic instructions we have in 8051. So first one, ANL, logical AND. So basically it will do the bitwise logical operation between the two operands we have, destination and source. For example, here you can see we have these two values. If I take the ANL of both of them, what will happen is we are just going to take the logical AND, bitwise AND between these two values. So 0, both of the values are 1, so here it will be 1, and other cases it should be 0. Okay, and this value should be saved in destination always. Okay, generally destination is taken as the accumulator. It can be direct address as well. Source operand can be a register or in memory or immediate. Next, ORL, similar kind of logic instruction, but here we are doing logical OR. Everything else, every explanation is similar like before. So for logical OR, we know that if at least one of the values is 1, the result is 1. So that means here it should be 0 0 1 1 0 1 0 0, right? So this should be saved in the destination. Next, XRL. XRL similar, just here we are doing the XOR operation. So for XOR operation, we know that odd numbers of 1 gives us 1. So that means whenever we have both of them 1, the value should be 0. Both of them 0, value should be 0. But if one of them is 1, value should be 1. So here we are going to get 0, 0. Here it should be 1. Here it should be 0. Here it should be 1. Here it should be 1. Here it should be 0, 0. And the value should be saved in destination. Another thing you have to understand, we can use this kind of logical instructions for single bits as well. This is supported. So for example, here we are doing ANL between carry and pin 2.7. Next, we will look into the details of compare instruction CJNE. So the instruction was something like compare and jump if not equal. So we are comparing these two operands. If they are not equal, then we have to jump to the label. So this was our understanding, but it additionally does another thing, which is it can actually indicate whether the destination operand is larger or smaller with the help of carry flag. So if destination is larger or equal to the source, then carry flag is equal to 0, and if destination is smaller than the source, then carry flag will be equal to 1. This is how it works. And what you have to understand, this particular instruction does that with the help of subtraction. So the values we get in carry flag is with the help of subtraction. Basically, whenever we do a subtraction of source from the destination, if the destination is larger than source, in terms of subtraction, carry flag should be 0 to indicate borrow is equal to 0. And if destination is smaller than source, basically minuend is smaller than subtrahend, then what happens? To indicate the value is negative, we have a borrow or carry is equal to 1. So similar thing happens for here also, but only difference is the value of destination and source will not be altered. As it happened in subtraction. In subtraction, we are always dealing with register A for subtraction, and after the subtraction happens, register A has the result, modifying the previous result, right? So this will not happen here. The values we have in destination and source will be intact, but carry flags will change to indicate which value is larger, destination or source. So let us look at one example to understand how it actually works. So here they're saying, assume that port 1 is an input port connected to temperature sensor. Write a program to read the temperature and test it for the value 75. So we have to check data from port 1 which is connected to temperature sensor, and each time we have to check that value with 75, whether that is equal to 75 or not. According to the test result, place the temperature value into the registers indicated by the following. So if temperature is equal to 75 coming from port 1, then we have to keep 75 to register A. If temperature is less than 75, then we are going to keep the temperature onto register 1. If temperature is higher than 75, we have to keep temperature onto R2 register. So how to do that? First of all, we have made port 1 as input by giving FFH. Then we are reading from port 1 and moving that value to A. Now we are going to compare the value we are getting as temperature with 75, whether that is equal to 75 or not. So if they are not equal, then we have to move to over, right? Compare and jump if not equal. So if they are not equal, we have to go to over. And if they are actually over, we can go to the next line skipping this label. So that will be short jump exit. So if they are actually equal, what happens? Register A already has 75 value, which was the task we have if temperature is equal to 75. So we don't have to do anything. We can directly short jump to exit. If they are not equal, then we have to go to over to fulfilling other conditions we have, right? Which are if that is greater than 75, we have to do one thing. If less than 75, we have to do another thing, right? So what they're saying here is jump if not carry, because we know after this instruction is executed, based on the value which is larger or smaller, carry flag will be set. So if here register A is larger or equal to 75 from here, then cy should be 0, and if a is less than 75, then cy should be 1, right? Now look at this command, jump if not carry. So jump if not carry means this condition, right? If not carry, we can go to this label next, and if not carry, that means the value we have in temperature which is stored in register A is actually greater than 75, and for the case of temperature greater than 75, we have to store the value onto R2, which is done here, right? And if there is any carry, then we will skip this label and move to this next line, which is meaning that our carry is equal to 1 and value is less than 75. In that case, we have to store the value onto R1, which is what we have done. Then we can short jump to exit. This is how it works. Next problem, here they're saying assume internal RAM memory locations 40 to 44H. 5 locations we have, they contain the daily temperature for 5 days as shown below. Search to see if any of the values equals 65. If value 65 does exist in the table, give its location to R4, otherwise make R4 is equal to 0. So we have 5 different RAM locations. There the values are actually saved, right? These values are actually saved. Now what we have to do, we have to search through these RAM locations, find out if any RAM location contains 65, which is actually correct. One of the RAM locations is actually storing 65, but we have to check that through the help of code. And if that happens, we have to store the memory location, RAM location, onto register 4, not the value but the RAM location. So let us look at the problem. First of all, because if there is no value equal to 65, we are not going to store anything to R4. R4 should be 0. That's why initially we are making R4 is equal to 0. Then we are taking the first RAM location to R0 to do indirect register addressing, and also we have 5 location. We have to do the loop, continue the loop for 5 times. That's why we are taking a counter, loading a counter onto R2. Then for comparison, we are going to keep 65 onto A, and then we are going to do the comparison. So here you see what we are doing. We are comparing the RAM location inside of R0, which is currently 40H. So inside of 40H location, what is the value currently saved? Comparing that with 65. So we are basically comparing 76 with 65. And if they are not equal, we will go to the next level. And if they are equal, we are going to go to this next line. So then what we will do, we will just store the RAM location. If they were equal, we were going to store the RAM location onto R4, which is 40H. But here currently, obviously, they are not equal. We are going to go to the next label that will increment the RAM location counter. So R0 previously was 40H, now it will become 41H. Then we are going to decrement the value inside of R2 basically for the loop and go to back again and compare with the value inside of 41H location, right? In this way, for each of the cases we are going to compare, and we will see that whenever we reach 43H, they both will be equal, and then we can skip this label. We will just move the value 43H, the RAM location of where this value is saved, to R4. Then we can short jump to exit because we have completed our task. Next we will look at rotate instructions in 8051. So rotate instructions allow program to perform a bitwise rotation, okay, right or left. So you will see how they actually work. So we have some of them here: RR, RL, RRC, RLC, this kind of rotate instructions. But one thing to remember here, always this kind of rotate instructions should be used with register A. So one example, let us look at the first one, rotating the bits of A to the right. Okay, so which is RRA. So what happens in register A, all of the bits will shift to the right by 1 bit, and also the least significant bit we have will move to the most significant bit, so kind of like rotating to the right by 1 bit. So you see, with this example we can understand we are moving 36H to A initially. You see here, this is the value 3 and 6. After we execute this instruction once, RRA, what will happen? Every bit will rotate to the right by 1 bit. So you see, this one comes here, this one comes here. In this, all the values are actually going there, but this value is actually going here. Okay, so in this way all the values are rotating to the right, uh, but the least significant bit LSB becomes MSB after this instruction. Each time you see same thing is happening, every bit is rotating to the right. Next, rotate left, same, just in left direction. So you see, after taking 72H onto register A, this is the value, right? And then if we execute RLA once, then what will happen? All the bits will shift to left by 1 bit in this way. Okay, and then uh, this bit will actually go to the LSB of the next one. Okay, so in this way it works. Then rotating right through the carry, same kind of rotation, but carry will also be included in this rotation. So what will happen? The value in carry will go to the MSB and a bit from LSB will go to the carry. In this way, every bit will shift through the carry. For example, let us look at this example. First of all, we are clearing carry. Now carry has value 0. Then we are moving 26 to A. So 2 and 6 and carry is equal to 0. If I use RRCA, rotate right with carry once, what will happen? Every bit will shift to the right, carry will also get modified. So what happens? This 0, previously this will come here, right? But all the bits we see are rotating to the right by 1 bit, something like that. And this least significant bit is coming here. In this way this is happening. If you look at the next one, you see all the bits are actually moving to the right here, and then this value is coming to the carry, right? So in this way, each time all the bits are rotating to the right, including the carry. Next one, RLC, rotating left through the carry. So just like RRC, but now the direction is left. So I hope you can understand. So carry, whatever value we have, will go to the LSB, but the most significant bit here will move to carry. In this way, everything rotates to the left through carry. Okay, so here you can see, first of all, we are setting the carry, which is making carry is equal to 1. Then we are moving 15H to A. So this is the value 1 and 5. Now if you execute RLC once, what happens? Everything moves to the left by 1 bit, so including the carry. So that's why you see carry is actually coming here. Then this is moving here. This is moving here. This is moving here. In this way, so this value is actually going to the carry. Okay, after all the movement happened like that. In this way, everything moves to the left through the carry. Now these kind of rotating instructions are very helpful for serializing data. So what is serializing? Whenever we send a byte of data 1 bit at a time through a single pin of microcontroller, that is serializing. So this is one example like that. This is our register A. We are just sending 1 bit at a time with the help of one pin of microcontroller, right? So how to do that? We use this kind of rotate instruction. We can look at this example to understand. So write a program to transfer value 41H serially 1 bit at a time via pin 2.1. Send the byte LSB first, right? So first of all, we are loading the value 41H onto register A. then we are loading 8 onto R5 because in register A we have 8 values, 8 bits, right? So we have to rotate for 8 times, as you will see. So if I actually execute this line once, what will happen? Every bit from register A will rotate to the right by 1 bit, including the carry. So the least significant bit will come to the carry, and all the bits will shift to the right, and whatever value we had at the carry will go to the most significant bit. That is not important, but what is important is if I execute this particular instruction for 8 times, what will happen? One by one, all the bits inside of register A, or all the values of 41H will come to carry one by one, least significant bit first, one by one. So that's why we have this 8 value, so that we can run this loop for 8 times, so that we can get all the 8 values of 41H which is stored in register A. So what we are doing? We are doing RRCA, then the bits are actually stored each time in CY, right? We are going to move that value onto pin 2.1. In this way, each time after each iteration of this loop, one bit from this register A will come to carry as well as come to this pin 2.1. This is basically what we call serialization of data. Next, similar kind of problem, but previously we had sent the data to a particular pin to outside. Now we are going to read something from outside through our read pin, and then we are going to store that inside of our microcontroller. So write a program to bring in a byte of data serially 1 bit at a time via pin 2.7 and save it in register R2. The byte comes in with the LSB first. Okay, so we are getting some data from pin 2.7 that will go to the carry and that then to the register. Here again we can use RRC. We are first of all loading 8 to R5 because we have to run the loop for 8 times. Then we are setting pin 2.7 to configure that as input. Then we are going to go to the loop. We are going to read from pin 2.7 and store that onto carry like here. So if I execute RRCA once, what will happen? The value stored in CY will go to the most significant bit of register A, and everything in register A will shift to the right by 1 bit. So in this way, each time we execute this line, this particular loop, what will happen? A value from pin 2.7 will come to CY, and that will come to the most significant bit through the help of RRC. In this way, after 8 times, all the bits will be filled up with data coming from pin 2.7. So this is how we actually serialize data coming from outside by reading. Okay, next we have swap instruction. This basically swaps the two nibbles we have in a register. Like you can see here, the upper nibble goes to the lower nibble and the lower nibble goes to the upper nibble, and it only works with the accumulator. Like here you can see, if I use swap, 72H become 27H. Now we will discuss about the conversion between ASCII and packed BCD. So you will see this is very useful and very important. But before that, let us discuss about ASCII codes. So what is ASCII? ASCII is just a character encoding standard to represent text in computers. Okay, so generally standard ASCII is of 7 bits. Each of the characters are represented using 7 bits. So that means in total we can represent 128 character. In 8051, because our registers are of 8 bits, what we do, we just add a 0 at MSB to make it 8 bit. So all the ASCII codes are actually represented using 8 bits in 8051. So here in this discussion we will strictly talk about ASCII characters 0 up to 9 and how they are represented, and we will try to understand how they can be converted into one form and another. So you see, these are the values here. The ASCII representation or code of those are basically, if you add 30 with that, you are going to get the ASCII representation. Like for 0, we actually send 30h. For 1 we send 31h. So in this way all of the values or the digits we have from 0 up to 9 can be represented just by adding 30 to the unpacked version of the value. Okay, so 1 can be represented in unpacked BCD like this. So upper nibble is actually blank, lower nibble is representing the value. In this way all the values are represented. If I want to convert that to ASCII, what I have to do, I have to just add this portion here, 000011 or 3 basically. If I do that, that will be converted into ASCII format. Okay, now if we understand ASCII, now let us understand why it is important to know how to convert between ASCII and packed BCD. Many times we will see in microcontrollers different sensors and input devices are connected, and how they actually send the data to microcontroller is in format of packed BCD. Okay, for example, we can talk about RTC, real-time clock. So it can actually generate time and day and send that to microcontroller. So the format in which it sends the data is packed BCD. And let's say if I want to show that data, the time and date, using some kind of display unit, for example LCD. LCD receives data in form of ASCII. So that means if I want to show the same date and time in LCD, I have to convert that value into ASCII, right? That's why oftentimes it's very important to understand how to convert from ASCII to packed BCD, and also from packed BCD to ASCII. We will try to understand that. Now let us look at the format we have. Like for the same value 29h, which is a packed BCD example. So this value is 2 and this value is 9, right? So if I want to actually convert that to ASCII value, what we actually need to get is one ASCII character or representation for 2 and another for 9, right? For 2, we know 2 can be represented using 32 for ASCII and 9 can be represented by 39. And we are seeing the binary equivalent of that here and here. So what we have to do is, if I get a value like that, a packed value, I have to output these two values to actually transmit that to LCD to show that, right? So how to actually do that? What we do, we actually take help of unpacked BCD whenever we try to convert packed BCD into ASCII, or let's say from ASCII to packed BCD. So what we do, we just unpack these two values we have in packed BCD into unpacked form. So for 2 we will have this value, and for 9 we will have this value. Then we actually add 30 with these two values to get the ASCII characters, right? So we will look at some examples that will be easy to understand. So here we will try to convert a packed BCD into its ASCII representation. So that value is actually 29. Let us look at the example. Assume that register A has a packed BCD. Write a program to convert packed BCD to two ASCII numbers and place them into R2 and R6. So 29, for 29 we have to get ASCII character for 2 and 9, right? So first of all, this value is moved on to A, and then we are moving that value into R2 because we have to do the calculation twice, once for 9 and once for 2. So that's why first of all we are storing the data onto R2, then we can do any kind of manipulation to register A. So that's why we have initially stored the value onto R2. Now we are going to take register A, and in register A currently the value we have stored is what? A is equal to 0 0 1 0 1 1, sorry, 1001. This is the value we have currently saved on A, right? And then here we are going to take the ANL with 0FH. So what is 0FH? 0FH is 0 0 0 0 1 1 1 1. When I take ANL, what happens is it will just mask the least significant 4 bits. So these particular 4 bits will become 0, and we are going to get this value here, right? So this is basically making our value into a unpacked BCD form. Unpacked BCD form of 9, right? Then with this unpacked form, we have to include 30H, or basically we are going to do ORL, logical OR operation. So this 30H, if I want to write that, it will be something like that: 0 0 1 1, then 0 0 0 0. So we are doing the current contents of A here, this one, with 30H. So if I do the ORL between these two value, the value we are going to get is 0 0 1 1, and this value will come as 1 1 0. So this is the value after this execution, right? And this is 3 and 9. 39H is what we are getting, which is the correct ASCII representation of 9 we have got for one thing, and that should be saved in R6. Okay, so that's why the contents of A is now saved in R6. Now again we are going to take the data from R2 which was previously saved. This value was saved in A, then again saved to R2 for storage purpose. Now we are going to convert these two into its ASCII format. That's why we are taking the value from R2 to A. Again here you see in A we have this value basically. So 0 0 1 0 1 0 0 1, this is the value currently we have in A. Then we are going to do ANL with 0 FO. What is FO? FO is 1 1 1 1, then 0 0 0 0. We are going to do the ANL between these two values. That will give us only the upper nibble, because here we want the upper nibble. We want to work with 2. Already we have worked for 9. We have converted it into its ASCII format. Now we have to just take care of this value. So that's why this value will come at the end, and the lower nibble will get vanished after this line, right? This is what we have got. Then we have to swap A, because this is not correct unpacked representation. Whenever we use unpacked representation, the lower nibble should be the value, BCD value, upper nibble should be blank. Here upper nibble is 2, lower nibble is 0, so we have to swap that. That's why we have this swap, and if I swap, it will just become 0 0 0 0, then 0 0 1 0. This is the value, and this is the correct unpacked representation of 2. We just have to ORL 30H with that, so like that. So this value, let us write that again: 0 0 0 0 0 1 0, then 30 0 0 1 1 0 0 0 0. If I do the ORL, upper nibble will keep this and lower nibble will keep this. This is 3, this is 2, so this is 32H, right? So we have got 32H, or the correct ASCII representation of 2. So that means we can save that value onto R2. So this is how a packed BCD 29 has been converted into its correct ASCII representation 32 and 39H. So this was example for conversion from packed BCD to ASCII. Now we are going to look at another example where we will convert from ASCII to BCD, or basically packed BCD. How to do that? So here we have two characters, 4 and 7. So basically we are showing 47 in ASCII. We have to convert that to packed BCD, right? So how to actually do that? Let us try to understand. So here first of all, we are taking the first character 4. If you just write it in this way using this kind of quotation, it will be represented as ASCII code. Okay, so basically if you look at what value is saved onto A after this execution, you are going to see the value is 34H. Okay, so A will have 34H. After that, let us write that 34H is what? 0 0 1 1 0 1 0 0, right? So this is 3 and this is 4, and then we are going to ANL 0FH. So if you do that, 0F is equal to what? 0 0 0 0 1 1 1 1. After doing the ANL, we are just going to get the lower nibble and upper nibble, or these 3 will be vanished. Basically this is the unpacked BCD representation of 4, which is what we want, right? Now we have actually swapped the values of A here. So this value is swapped because basically we want to show 4 and 7 into one BCD or one 8-bit value, 47. So in that case, the result should be something like this. 47H is what? 0 1 0 0 and 0 1 1 1. This is the packed representation of 4 and 7, right? So that means this value should be in upper nibble. That's why we have moved that, and now we are going to work for 7 and merge with this one, right? So we have moved this value onto B because now we are going to again work for converting ASCII character 7 using with the help of register A. So that's why we have moved the result we have got here onto B. So it will be in B. Then we are taking 7. So A currently has what? 37. 0 0 1 1 0 1 1 1. This is 7 and this is 3, the ASCII representation of 7. Then we are going to again do ANL. So ANL with 0FH, same thing, 0 0 0 0 and 1 1 1 1. It will just keep the lower nibble, so 0 0 0 0, then 0 1 1 1, or this is the unpacked representation of 7. Now what we can do, this value, this unpacked value and this value, these two values can be merged together, right? This is saved in register A currently, and with that we are going to merge the value of this. So basically we are going to do ORL. So if I do ORL between these two, let us write this value. Let us write this value first. So 0 1 0 0, then 0 0 0 0, and let us write this value. This is saved on B and this is saved on A. So 0 0 0 0, then 0 1 1 1. This is saved on A, right? If I do the ORL between these two values, upper nibble will come from here and lower nibble will come from here. So this is the value after doing that, and result will be saved on A, right? So this is 4, this is 7, the correct BCD, packed BCD representation of 4 7 in ASCII. Okay, the last topic, checksum for error detection. So whenever a sender transmits a data to receiver because of noise or hardware faults or any kind of communication error, there can be situations such that the data is corrupted. There is some manipulation in the data. So that is why generally an error detection method is required to understand whether the data we have got is correct or there is some corruption, right? So checksum is such kind of error detection method for detecting error. So what we do, checksum processes actually calculates a thing called checksum byte. So this is an extra byte which is tagged along at the bottom or at the back with all the data we want to actually transmit. So how this is actually calculated, let's say if I want to transmit a series of bytes, let's say 5 or 6 bytes we want to transmit. What we do, first of all, we add all the bytes together and then drop the carries we get. After doing all the calculation, if I get any carry, it should be discarded. Only the 8-bit result should be considered. Then we are going to take the 2's complement of that value. That will be the checksum byte of the series of bytes we want to actually transmit. And this checksum byte will become the last byte of the series of data to be transmitted. Okay, so when the receiver receives that data, how can he detect whether the data is correct or corrupted? So what he will do, he will just add all the bytes he has got, including the checksum byte. He will add all the bytes, and the result should be 0. If after the addition result is 0, that confirms that there is no error, that data is correct. And if there is any value other than 0, that basically indicates that there is some error in the data. This data should be transmitted again from the sender. Okay, so let us look at one example that will clarify how it actually works. So here in this example, they are saying, assume that we have 4 bytes of hexadecimal data, these 4 values. We have to find the checksum byte. Okay, so first of all, let us try to find that here. So this is hexadecimal addition. Just like before, we have to add all the values. So 5 plus 2 plus f is equal to 15 plus 2, which is equal to 24. So if that is 24, we have to discard 16 from that. So if I discard 16 from 24, 24, 16, what we are going to get? 8, right? So 8 should be there. 8 should be there, and we can just remove this portion, right? So that carry should be coming here, and now what we have, 1 plus 2 plus 6 plus 3 plus 5, which is equal to 17. So this value is equal to 17. Again, we have to discard 16 from that. So 17 minus 16 is equal to 1 here, and the carry should be going to the next stage here, and we are going to get 118H as the result. This one is actually carry, right? So we have to consider this portion only, and we said for this particular portion here, what you have to do, we have to take the 2's complement of that will be the checksum byte, right? So what is 2's complement of 18? 18 in terms of binary value should be what? 0 0 0 0, sorry, this should be 1, and then 8 1 0 0 0. 1's complement is 1 1 1 0 0 1 1 1. Then add 1 with that will become what? 1 1 0 1 1 0 1 1 0 1, and this will come out as it is. So this is 8, and this value is what? This is 8 4 2, so 14 is E, right? So it should be E. So the checksum byte should be E8, so which is actually added here. So if you look at the next problem here, apart from the checksum operation to ensure data integrity, so E8H is the checksum byte we have found out for this series of bytes we have. And actually, whenever it is transmitted to the receiver, we are going to transmit the 5 bytes. These 4 bytes and the last byte should be E8H, and this is the data that should be received by the receiver. And receiver will add all the bytes here and look at the result. If the result is equal to 0, that will signify fact that the result is correct without any kind of corruption. So let us try to do that. So if I add all the values, what will be the result? 5 plus 2 plus f is 15, so 15 plus 2 plus 8, so which is equal to 32. So now here we have got 32. Understand that 32, here we have to discard 32 base 16 calculation. That's why 32 is twice of 16, so that means we have to discard 32 from here and we have to write 0 here, and at the next stage we are going to get 2s carry. Okay, this is how it will work. So we have to remove that. Now we are going to add all the values here. So again here 2 plus 2 plus 6 plus 3 plus 5 plus e is equal to 14. So if you add all of these values here, again you are going to get 32, and 32 again is twice of 16, so that means we have to discard 32 from here and keep the 0, and the 2 will come as the carry here, that will come here. So this 2 is actually carry after 8-bit, so we can again omit this. We don't have to consider that. The result is actually 0, right, after performing the addition. So that means the data we have received is correct without any kind of corruption. Now in the third example, they are asking if the second byte 62H has been changed to 22 when it is being transmitted, basically, then show how checksum detects the error. So basically whenever the data was transmitted, they are saying because of some corruption 62 has been changed to 22, and now if the receiver finds these values, what problem there can be, that is what they are asking after calculating the addition. So let us try to calculate this. So 5 plus 2 plus f is 15 plus 2 plus 8. So here we are getting 32. If you add all the values, you are going to add 32, get 32. So again you have to keep 0 here, and 32 will be considered as 2 as at the next stage. So here again we are going to add all of the values. 2 plus 2 plus 2 plus 3 plus 5 plus 14, so which becomes 28. So if you add all the values in this stage, you are going to get 28, and you have to discard 16 from that. If you do that, you are going to get 12. So we have to write 12 or hexadecimal equivalent of that, which is C, and we are going to get 1 here, that will come here. Even though we don't have to consider this carry here, no problem, but still the value we are getting for the 8-bit here after doing the addition is C0, not all zeros. So that means in this case there are some corruption in the data we have received. So in this way we can detect error by checking checksum byte. At the end of this lecture, here we will try to look at two assembly programs. One of them is the checksum program. So here, whatever we have discussed theoretically in the last page, we will try to implement that in assembly. So in this code, I will try to explain part by part what each part is doing, but before that, I think we can initiate with this portion. So you see the values we want to actually transmit or want to save, these are actually saved here in code memory 25H, 62, 3F and 52. You can check that these are the same values we tried to explain in the last example here. So these are the values which are stored in ROM location starting from 400H. We also have given specific names to those using assembler directive here. Define them as constant. So data ADDR, this is same as 400H. Okay, then we have another two constant, count and RAM ADDR. We will discuss about those as we move on, but here we can already say that one of the tasks we will have here is to actually move the data we have in code memory onto RAM locations. So we will try to store those data in RAM locations 30H, 31H, 32H, 33H. So in these 4 locations we will try to save these 4 values. That's why we have this particular constant here. And this is a modular implementation of the code. So that's why you see we have three different subroutines. First of all, copy data, to copy this data from ROM location to the RAM. Then next one, cal checksum, is for calculating the checksum byte from these 4 bytes of data. And then the next one, test checksum, is after calculating the checksum, if we have transmitted the data, how we can actually test the checksum to figure out whether the data is correct or not, okay, whether there is any corruption or not. So that's why you see, starting from 00h, we have just called these three subroutines, then we have given an infinite loop here, short jump $sign. So first of all, let us try to understand this subroutine here, copy data. So we will have to move the data we have in code memory to RAM locations, and we will start from RAM location 30h. That's why we have given this name. So first of all, we will move our data address, which is 400h, or the starting location of the data stored here, to DPTR. Then we are going to load the RAM address onto R0, because we are going to do indirect register addressing, and because we have 4 bytes of data here, we have to do this thing for 4 times to load the data onto RAM. That's why we have given the value 4 onto R2. So this count is basically 4 here, understand? So now we are going to start the loop. First of all, we have cleared register A. Then A plus DPTR is currently storing what? 400h. A is 0 and DPTR is 400h. So we are going to fetch from here basically 400h location and move that to A. After that, what we are going to do, A is currently have 25h. So that 25h should be moved to the first RAM location 30h. So that will be done with this particular line. Then we are going to increment the DPTR, that will become 401, and R0 will be incremented, so that will become 31. And then we are going to again go to H1 for, so this will happen for 4 times, and at the end of execution we will see whenever we reach return 30, 30, 31, 32 and 33, these 4 RAM location will have these 4 values. Then what we will do, we will try to calculate the checksum from these 4 bytes. So that's why again we have to load from the RAM address where we have actually stored the 4 values. So starting from RAM address 30h location, we are moving that to R1 to do indirect register addressing, and also we have loaded R2 because we are going to run this for 4 times. We are clearing the value of A because in the loop we are going to add the values. You know, in the previous example we said that we are going to add all the values first of all to calculate the checksum byte. Add all the values, whatever value we get, discard the carry, then take the 2's complement of that. That will be our checksum byte. So similar thing is happening. First of all, we are clearing A, then adding whatever we have in 30h location. In R1 currently we have 30h value saved. So in 30h RAM location, the value we have saved, that will be added with A. Then we are going to increment the value of R1. So 30 will become 31. Again we are going to go to H2. Again we are going to add. So in this way 30, 31, 32 and 33, in this 4 location, whatever data they are saving, actually they are saving these 4 values, they will be added together with this loop. And because we are not considering carry here, carry will be discarded automatically. After doing this thing, when we get out of this loop, register A will have the result of addition, right? Now what we have to do, we just have to take the 2's complement of that. That's why we take the CPL complement, then increment by 1. So after that, so after this line, after execution of line 31, register A has the checksum byte. Now what we want to do, we know that starting from 30 to 33h, these 4 locations are saving these 4 values, right? What we want to do, in 34h location we want to save the checksum byte. So that's why we have this line. Understand that whenever we execute this loop, in the last phase, in the last iteration, R1 will get incremented from 33 to 34 here. So when it gets that, when we get 34H inside of R1, if I look at here, obviously R2 will become 0 because already 4 times the loop has been executed, and now the value stored in R2 is equal to 0. So it will come out of the loop without going to H2, but R1 has been incremented to 34. Understand that. We have done this for 4 times and all the 4 values have been added, but afterwards this R1 will get incremented to 34H. So if that happens, that means when I run this line here, A is currently saving the checksum byte, and that will be saved on to 34H location of RAM. Okay, so from 30 to 34 we have the 5 bytes we need for sending the data, including the checksum, and then we can return. So this is for calculating checksum. Then finally, test checksum is to test the checksum, adding all the values as we have seen, including the checksum byte, and finding out whether that is 0 or not. So that's why first of all we are going to load the RAM address, initial RAM address to R1, which is 30H. Then we are going to load the value 5 onto R2. So count plus 1. You see, because now we have 5 values on 5 different RAM addresses, including 34H. That's why we have to count for 5 times, not 4 times. Basically, loop has to be iterated for 5 times. So again, here we are doing the same thing, clearing A, then adding all the values. So whatever we have inside of 30H, we are adding that to A, incrementing R1, then again going to the loop. So in this particular portion, starting from 30H location to 34, 5 times this loop will run, and the 5 values saved in these 5 RAM addresses will be added together, and carry will be automatically discarded without any issue. So if we add all of this value, currently after execution of this loop, register A should contain the result of the addition. If that is 0, then we can say there is no corruption in the data. If the value is not 0, we can say there is some corruption. So that will be done by this line. So jump if 0, jump if accumulator is 0 to label G1. So G1 is what? It will just say the data we have is good, or this ASCII character will be sent to port 1 to indicate that data is good. And if that is not the case, we will go to this line, which is to send this ASCII character to P1, indicating the data we have is bad. Okay, so then we can just move on to over, which is the end of command. We can again move on to the initial line basically. So in this way, this code works in a modular fashion. Okay, the last one. So here this program is for converting a binary to its ASCII representation. If you look at the statement, here they're saying what we will do is we are going to get an 8-bit binary data from port 1, and we will convert that to decimal digits. So I think we have already seen an example like that. So getting a data from port 1, the range is from 000 up to FFH, so 00 up to 255 in decimal, and we had to convert that to decimal. If you remember, we had to divide for 2 times, and then we got the values. So similar kind of approach will be given here, and then what we have to do with the decimal number, we have to convert that to ASCII digits. Okay, so we are going to get at most 3 digits we have to convert for each to its ASCII representation. Okay, so how to do that? And also they are saying we are saving low digit in lower address location and high digit in higher address location. This is referred to as Little Indian conversion. So we will see how that happens. So we are going to store the lower digit in lower address or RAM location basically, and higher digit will be saved on higher address location. So we will look at that. So here also we have actually given name to these constants. So 40H is the RAM address and 50H is the ASCII result. We will see what actually happens there, and we have taken a counter of value 3. Now here also we have two different subroutines, and these are called here and then short jump. So first of all, look at the first subroutine, which is converting a binary to its decimal equivalent. So I think similar kind of problem we have already seen in one of the examples. Here what we are doing, we are actually taking 40H, the RAM address, to R0 so that we can do indirect register addressing. Then we are taking data from P1 to A. So we are reading from P1. I think we should actually give FFH to P1 first so that we can make port 1 an input port. Then we can read from here. So we should actually include that here. Then after reading from port 1, currently register A has a value range can be 0 to 255 in decimal, and that value has to be divided by 10. That's why we have this instruction. Then we are going to store the remainder in RAM location, first RAM location, which is 40H. Then again we are going to increment R0, so 40 will become 41. Again we are going to divide whatever we have inside of A by 10. Right here we have done that. Then again the remainder will be saved in next location 41H. Then again we are incrementing RO, so 42. Then keeping the quotient we have that is going in 42. So 40H, 41H and 42H, these are the three locations. This is saving the least significant digit, then this is saving the next one, this is saving the next one. In this way this is actually happening. You can look at the previous example. I think it will be cleared up. So after that we have to convert this decimal value we have stored in three different RAM location. We have to convert each of them into its ASCII equivalent. So that's why again we have stored the initial RAM address, which is 40H, and we have loaded 50H, basically another RAM location, I think, stored that in R1. So we are going to actually store the ASCII equivalent of these three values onto 50H, 51H and 52H location. That is the idea, I guess. So for that we are initially storing the counter because our loop will run for 3 times. And then what we are doing, so we are taking data from this indirect addressing. This is storing 40H. So that means from 40H location we are going to move one data into A. Then we are going to take the data. Basically in 40H location one of the decimal values is stored, and that value will be ORed with 30H. That will convert that to its ASCII equivalent. Then what we will do, we will move that value, the ASCII value, onto the RAM address pointed by R1, which is 50H basically, right? We have given 50H, so in 50H location that value will be saved. Then we are going to increment R0 and R1, so 41H, 51H it will happen. Then again we will go to the first line of the loop, again do the same thing, try to convert the value into its ASCII value and store that to 51H location. So in this way 3 times it will happen, and in 50H, 51H and 52H the 3 ASCII values will be saved in Little Indian convention. So this is how this code works. I hope you understand, and that's all for this lecture. Thank you.